Hi everyone. Let's chat about assignment 2. I struggle every time. But just before we did that, I wanted to touch on a really quick point that someone asked earlier where they said something like, oh, is this because swaps are cheaper than comparisons or comparisons are cheaper than swaps? Or something along those lines. I think, without getting into the detail of it, and I know some people here are passionate about this area, is that you have to understand, I guess, that the way a processor works, like a computer processor, is that um, it does an operation, and that operation takes a step, like a moment in time. Like we call it a cycle or something like that. And adding one and one is like that's a cycle. Then adding, one minus one minus two, it's like plus and then minus. Like these are all like steps and stuff. And they're kind of steps in the way that we think about it when it comes to time complexity. They're when we look through a program and there are steps. There are some things that modern processors are optimized to do, such as, I think I've given this example back in week 2, is like multiplying really big numbers together. So most modern, oh god, I can't even remember, but it's like, in general, it's like a computer is able to do 55 times 54 instantly. It can do that as quickly as it can do 2 times 3. But like, think about it here. It's like your brain can't do those two instantly, can it? Like your brain has a process that it follows with this first one where we multiply this column and then we carry the 1. And you could say that the way your brain does multiplication might be O(n) squared or something, right? And the way that your brain does simple multiplication might be O(1), and the way that your brain does addition might be O(n). Okay, now there's a reason that we don't look at these operations on a computer and think, well, when we multiply two ints together, is that constant time or is that n squared? And that's because processors, like literal CPUs, are designed to do certain operations really effectively. I'm not an electrical engineer and I'm not going to get into that, but essentially with circuit design, a lot of it comes down to how you do things in parallel. So it's like, take addition here, right? You can do this operation nearly instantly if your computer is capable of doing like all of those column additions at the same time. Because then when you add them, it just goes pow, like it's just like done. Did all the columns, carry the 1, done. Basically constant time, same complexity, same number of steps or clock cycles per the size of the number. There are lots of operations on a computer that you can't do instantly, such as looping through an array or shifting an array, right? Like a processor isn't really great at just shifting an array. But you know what? It could be. There's nothing stopping that. There's no rules of physics that stop that. I read this great Quora article the other day about Quora, Tesla, fastest chip or something. I get these Quora emails. By the way, I don't know. I don't know when I ended up giving Quora my email by accident, and I really glad I did because I got all these cool things. And I remember this was really interesting because they were basically like, Tesla were claiming they're like, we have the fastest chip in the world. We have the fastest computer for like self-driving cars. And someone asked the question, they were like, isn't there like graphics cards and stuff really quick? Like, surely there's higher end graphics cards than a Tesla. Like, surely like the computer in a Tesla, like a car, is not, cheaper than, not faster than all the other graphics cards and all this stuff. And the general answer for this was like, look, the Tesla chip is really good at doing what it needs to do. Basically, like if you think about your code and you think about like, if you were writing code, maybe a quicksort or something, and you knew that like 50% of all the code you were writing was doing the same operations, if you knew that you were doing a whole bunch of array shifting, for instance, and array shifting is O(n), you could go and design a chip or a CPU or something or a GPU that specifically can do that operation in constant time. It's like you can like fine-tune design a chip. So it's like, I think this is just something to keep in mind as you think bigger and broader than Comp 2521, which is like, this world of algorithms is not done in a vacuum necessarily, right? It's like there are certain algorithms that behave differently on different processors. I'm sure computers many, many, many years ago, you wouldn't consider large number multiplication to be a constant time operation. there's lots of things that kind of change like that. So that's just something to keep in mind, because the point here is that the only reason that some things like, you know, multiplication or certain types of swapping or function calls or whatever else are O1 is not just because they're only one step of work to do. It's because a computer processor is capable of doing all of those steps in like one click because of how it's designed. And, you know, you'll see that will change in the future. Different chip design. I mean, that's the whole point of a graphics card, right? Like, I have a computer here. It has a graphics card in it and a CPU in it. They're two different processors. They do different things, and they're good at different things. That's why people end up using all these graphics cards for cryptocurrency mining and destroying the world and stuff, because, you know, they're fast at a particular type of operation. They can do some operations in, you know, to use an analogy, they can do some operations in ON time that a normal CPU would take N squared time, right? So there's a lot of stuff that really depends on chip design. Anyway, that's a random segue for 6 minutes. Let's talk about assignment 2 again. I don't actually have a ton to talk about here. I hope I haven't made this out like it's some big dramatic thing. But we kind of talked about part 1 and part 2 last week on Thursday, I think, and we talked about how part 1 is essentially just implementing Dijkstra, except your predecessor's array is not just the parent, it's like a list of parents, because you could have instances where there's multiple equal parents. And the examples, I told you in lectures that the examples we had in lectures were all where there was a distinct shortest path, whereas if you have multiple shortest paths, you need to do Dijkstra with that addition. We then talked about part 2, which was around finding closeness centrality and betweenness centrality, and how these were, you know, not the easiest things in the world, but fundamentally, you're just trying to plug stuff you've gotten from part 1, potentially, or using part 1 to generate some information, and then plug it into some formulas and calculate some things. Waleed says in the chat, the other day I was doing this assignment, and one line of my code that I changed brought my runtime down from 8 seconds to 0.1 seconds. So an 80 times increase in speed. And yeah, it does. It really makes you think about how performance works. Did I tell you the story about... I think I told the tutors this. Did I tell you the story about Richard Buckland and his old computer? If I didn't, I'll tell you after. Just answer me in the chat if that rings a bell. But so the third part here is a little bit more involved. But still fundamentally, it's mainly just about taking algorithms that you find online and applying it to your code. So part 3 is about discovering community. So community and clustering is this kind of idea of like, where is the dense, like where are things dense, where are things close? And if you're struggling to understand what they mean by community in this piece of text here, it's like community is referring to, like, if you got Sydney and you mapped everyone out in Sydney as a node, every person, and then you put an edge between every other person, say, you could find communities by looking where people are the closest together, where there's the most people close together in a given area. And you'd find communities or clusters around, you know, train stations where there's dense housing in the CBD, Parramatta, Penrith, like Chatswood, Hurstville, every other, don't want to get into every suburb in Sydney. You'd find all these different kind of places. And this is what we mean when we're looking for clustering or community. And there is an algorithm called the Hierarchical Agglomerative, I always read it but never say it, Agglomerative Clustering, HAC, which discovers communities in a given graph. And then we're looking at a Lance-Williams algorithm, which is essentially another similar algorithm on the same topic. And we're going to talk kind of loosely about how this works. We don't really need to like go crazy on it because it's pretty well described online, but I don't know if I care much about this page. Yeah, okay, so Um, hierarchical clustering is essentially this algorithm here, or what is it? Yeah, hierarchical agglomerative clustering is where you might look at a graph like this and assume these are, say connected. These are all nodes in a graph. Yeah, something. Um, and you want to start figuring out like how close they all are to each other. And the idea with clustering is that you want to take a graph that might look like this and turn it into something that looks like this. And what this graph here is trying to represent is it's trying to represent how close things are. So what it's trying to say here is that if you were to group B and C, like out of all of these, you would first group B and C because they're the closest. But D and E are equally close. Right? Both of these are two equally close. So the first grouping we could make is between B and C and D and E. So we kind of group those two things together. And think about this kind of output here as like a level where this is level 1, this is level 2, this is level 3, this is level 4, and this is level 5, right? So as you go from top to bottom, they're kind of like levels. So we could group B, C, D, and E. Okay, and what you do is, once you group B, C, D, and E, as far as, let me put this back in Paint. Oh God. As far as you're concerned, they're now kind of grouped together for the rest of analysis purposes. So it's like this first one, you're trying to say which are the most highly clustered or close together things out of A, B, C, D, E, and F. And once you realize that B and C and D and E are equally clustered, you then turn it into this thing. Then the next question you ask yourself is which are the most clustered between A, B, C, D, E, and F. So once you group things together, you kind of treat them like one entity from then on. So if I was to go back to this diagram, it's like, okay, well, how many effective nodes do I have here? And I have to think about this like I have 4 nodes now. 1, 2, 3, 4. Okay. Which is the next closest one together? Well, you can see that with your eyes. Like in this case, we're using distance as a real meaning of like edge cost here. And the DE node, the new combined node, and F are the same thing. So the next thing I'm going to do is combine DE and F, and then I get DEF. So the next question I have to ask myself is, what's the next thing I would group between A, BC, and DEF? So kind of on this diagram here, we've started to draw lines around these, where the first line we drew was around BC and DE, and that's where we ended up with 4 nodes, and now that we joined F to it, we've kind of got this new, like not a new graph, but like a new way of thinking about a graph, which is that we have 3 nodes. Okay? And then which out of these 3, how do these get combined together? Well, clearly these 2 are the closest, so then we end up with BCDEF because those ones got combined. And then we have this here and that here, and then these ones are combined. And that's how we end up with this kind of structure. So what you call a dendrogram, and it's just a way of grouping things. So you can actually kind of see how, as you go from, the very outer part here towards the end, you get into like deeper and deeper, closer and closer communities. So each level you go up is like referring to a cluster here. That's what hierarchical hierarchical clustering. Yeah, and it's the agglomerative. I'm gonna give up on this stuff. Agglomerative approach. Yeah, and Waleed says this would be interesting to show relations between best friends, close friends, friends, acquaintances, strangers. Yeah, exactly, stuff like that. D-Aurora says, anyone done Elec 111 last term? This reminds me of mesh and nodal analysis. Yeah, it does kind of feel like circuit analysis, doesn't it? Where you're grouping different circuit components together and treating them like they have some kind of aggregate voltage or current or something like that. So, no, I was joking when I know it's hierarchical. I was just being funny when I referred to it as something else. Sorry, apparently not very funny. So that's the gist of it. There's a couple of videos that have been linked here. This is not, I didn't write this assignment first, so There's some stuff on agglomerative clustering where they can talk through it. I mean, to be honest, like, this is useful, I think, to really step through it. And but they just show you the same kind of thing. It's like, here's my graph. Here is how I would represent it as a dendrogram. This is what agglomerative clustering is, and how I'd represent it. And again, this just shows you a sense of, you can see again the levels here. Notice how there's very particular about where things actually join. So the higher up they join, the less close a particular community is. And then there's a couple other videos which we might loop back to in a second. So Kevin has done a good job at simplifying this logic compared to previous terms assignments on the similar topic. So your life's a little bit easier because of Kevin, which is really good. So what we want you to do is try and develop a dendrogram for your graph. So you've kind of got this graph which you've been, part 2, you've got all these nodes and stuff, and you're dealing with closeness, centrality. You've got your graph, and we want you to produce a dendrogram, not like a visual diagram. We want you to be able to essentially produce a structure based on the Lance-Williams hierarchical agglomerative clustering algorithm, which is similar to what we've just kind of gone through, but I will talk about that in a sec, which follows this logic. And thankfully this logic is relatively straightforward. I remember the first time I read this at the start of term when we were talking about assignments, and I was like, oh, this wasn't as bad. This wasn't as bad as it looked. So, firstly, if you have a graph, I wonder if I have a graph example that isn't trivial. What do we have here? Yeah. So, let's just say you have a random graph. The first step of the algorithm is that you calculate distances between each pair of vertices as described below. So you calculate the differences between all of your pairs of vertices in the graph, which kind of basically, like, you need to make sure that you have weights between them, right? Because that's how clustering works. It's clustering, you need to understand how close things are, right? Then what they're saying is create clusters for every vertex, and each vertex begins as its own cluster. Now, I think a better way to kind of think about this is actually probably with the diagram we looked at on the Wikipedia page. So I might actually take this one, and we can start with here instead. This might be a bit easier. Is we have this diagram here, and what we're saying is, well, firstly, you need to look at all the distances between the nodes. So let's imagine that there's distances between these nodes here. There's edges between these nodes that we can't see. The next step is that you create clusters for every vertex in the graph. Okay, that makes sense. So I'm going to create a cluster here, a cluster here. A cluster is a collection of nodes, or a set of nodes like this. So I create all my clusters. Let's call this like, these are like the level 1 clusters here, the blue ones. Okay, so I put a cluster around everything. So I've got, for n vertices, I've got n clusters, and each cluster contains one node. The next thing is let the distance, Ci, Cj, represent the distance between two clusters, which right now is effectively the distance between two nodes. By the way, I know I have said, oh, we're going to finish early today, but every time I say that, we don't. I'm sorry. So we let the distance between two clusters represent the distance between two nodes. Yes, that makes sense. So if I want to say what's the distance between these two clusters, that's all that really means. That's just a mathematical description of it. And then we keep applying this algorithm until there's only one cluster remaining, which is essentially what this is here, right? We keep applying it until there's only one cluster remaining. We find the pair of clusters with the smallest distance between them, right? And if there are multiple alternatives, you can select any one of those pairs of closest clusters. So we look at our clusters here, and we say which ones have the smallest distance between them. And the answer is B and C, say, for instance. Okay, so we found the ones with the smallest distance. We want to remove those clusters, Ci and Cj, from the collection of clusters and add a new cluster that contains it. So essentially what that means for us is that we want to kind of get rid of this. And now we just have this like kind of one cluster that's just called BC. So there's no more sense of like we have a B node and a D node, because in two separate clusters, we actually just like combine them together and it's just one cluster now. It does actually contain the nodes in it, but from a cluster perspective, this is just one cluster. Then, update the dendrogram. Then we have to calculate the new distances. So the point here is that, like, you could imagine, A to D here might have a distance of 5, and A to E might have a distance of 6, and, D to F might have a distance of 4, and all this stuff. When you combine two clusters together, because you're kind of abstracting it into a single cluster, you're going to have to go and recalculate all the distances. And what I mean by that is previously, you would have had B might have a distance of, say, 4 to D, and C might have a distance of, say, 4 to E, but then C might have a distance of 5 to D, and C might have a distance of 5 to E, right? These edges all would have been here. So you think, okay, well, these don't make sense anymore because I've combined my nodes together and I just have one. I've combined my two clusters together and I just have one cluster now. So the next step after we've combined the cluster is that we need to recalculate all the distances. So we need to recalculate this distance and this distance and this distance here. So now this might be something like, say, 4.5. Maybe it's like an average between them. It doesn't, whatever it is. And then this distance here might be the same distance that B was. So this might just be like 6 or something. So whenever you combine clusters, you have to recalculate all the edge costs or the distances outbound, inbound from that particular cluster. And we do that using the Lance-Williams formula. So the Lance-Williams formula comes in here to help us actually figure out what that distance is. And you can see that. So I hope that makes sense. Firstly, it's kind of like where this whole Lance-Williams things come in is like, okay, well, I've got this cluster now that consists of two nodes. So how do I tell what the distance from BC, this abstract cluster, is to D? It makes sense when it's a node because it's all just edge weights. But it's like, how do I do this? And the Lance-Williams formula tells us that the distance between one cluster and another cluster, or in this case, say a cluster Cij to another cluster, or a node CK, is alpha times the distance between Ci and Ck, alpha I, alpha, beta, gamma, blah, 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 determined by the chosen. However, given a specific, we can simplify. Like, without getting into it, it's kind of like the Lance-Williams formula says that, and I'll try and draw this out separately over here. If I have a node over here which is B, and then I have a node over here which is C, and then I have something here which is D. Previously, you might have had edges between these that were like 2, 4, and 5. Okay? And then when you cluster them, I create my clusters like this, and then as part of the hierarchical agglomerative clustering, I combine my two clusters and I get this. The real question now is, what's the distance between these two clusters? What's this new orange line's weight? And the Lance-Williams formula says the distance between one of my clusters and the other of my clusters is either the minimum of the distances of the underlying nodes or clusters, or it's the maximum. And like, they're just two different ways of viewing it. And I'm pretty sure in your assignment you have to have functions that do either. But the point is, if you're using like a single linkage method, then you would say that the distance between these is 4. And if you're doing a complete linkage method, then the distance between these is 5, like that. So they're just different ways of trying to get the specific new cluster distance between things. And yeah, that's it. You go and you implement this inside of this particular ADT. So this ADT here, it wants you to take in a graph and produce a dendrogram. And it asks for a method, and that method is either... sorry, let me just grab the file. You can see that the methods available are either like they're hash defined just as numbers. There's like the single linkage or the complete linkage. So when someone calls this particular Lance-Williams hierarchical agglomerative clustering function, you get given a 1 or a 2, which tells you what kind of formula to use. Whether to use this one or this one when you calculate the clustering distances, the new cluster differences. You can also see that it returns this type dendrogram, which, as you can see here, is a data structure that is kind of reminiscent of a binary tree, because essentially, I mean, it kind of is a binary. Well, it's not a binary tree. It's a branch factor 2 tree, because that's all a dendrogram is. Like, if you go and have a look at this on the Wikipedia page, this is just a tree. You wouldn't call it a binary tree because it doesn't have a sense of order, but it is a tree nonetheless with a branching factor of 2, and that's what you see in these things as well. This dendrogram that's been produced here is just a tree. So the whole point of part 3 of assignment 2 is to basically take a graph and produce a dendrogram, or a tree, where that tree is how things are clustered. And you generate that tree just by following this algorithm here. So that's that. I actually think, again, it's quite well prescribed. I'm not going to lie, like, I haven't done either assignment 1 or assignment 2, but like assignment 2 for me, if I was a student still, seems less scary at a glance. It doesn't seem easier. It seems like more code to write, but it seems like it's more like clearly specified what to do. Like, the process is kind of given to you in a lot of this, which is really helpful. And I'm hoping that actually translates for you, and it's quite manageable. But Diorora says, would we make our own ADT for a cluster? I think I've answered that. Yeah. So would we make our own ADT for a cluster? I don't know if I'd say you need to make your own ADT for it. What I'd say is that a cluster is just a concept used to generate the dendrogram. Like, someone has a graph, they ask for a dendrogram. Input, output. That's the ADT. A cluster is just a way of thinking about the nodes as you're processing it. So you don't need to like make a like an ADT for it, but you'll probably want to have, I would guess you'd want to have some kind of struct to help you manage multiple nodes, maybe, but the tree might do that for you. Suddenly now part 3 sounds a little harder than I thought, but like, it's like you'll have to do something about that. Like, that is a bit of the complexity, but you don't need to think about it like an ADT. Yeah, there are some parts of this assignment that are hard. I'm not trying to give you the impression again that this assignment is easy. It doesn't look easy. It looks like it would take a lot of time. The thing I was saying was that I think what's helpful about this is that there's a lot of stuff that's very well specified, because I know with assignment 1 there are a lot of students that were kind of throwing their hands up in the air being like, I have no idea what to do at the lower end of the course, so I'm hoping that because it's more specified, it takes some of the pressure off in that way. Yeah, part 2 is conceptually a bit harder, yes, because it's the whole reachable from S thing that makes it hard. Anyway, are there any last questions about assignment 2 before we wrap up? Yeah, I mean, I'll just really quickly, it takes all of 60 seconds. The story I wanted to tell you is that it's probably somewhere out there on YouTube. If someone finds it, that would be cool. But there's a Richard Buckland video out there somewhere where he used to take this course a long time ago, and he demonstrated the importance of smart algorithms. And I can't remember exactly what he did, but he basically got this is all made up, but it's the same concept. He got like a n-squared algorithm, and he ran it on like his really new MacBook. This was like 10 years ago, and he put it up on camera. And then he got like an old like 1985 DOS style terminal. It was a really old computer, and he ran like an n log n algorithm on it. And he ran those two things side by side. And then basically he just like started the algorithm as it processed numbers. Think of it like a factorial generator or something like that, or something that, got really slow as it got quicker. And, it was a really interesting demonstration because he basically showed that, the new MacBook just like smashed through the first 20 numbers, and the other one was quite slow to get through it. But as the algorithm got, more complicated because it was non-linear for like bigger numbers, like it was only a matter of 30 seconds before the really old computer, the really old crappy computer, was actually processing things faster than the new computer. which is, just like kind of another example of like it's good software will always compensate for bad hardware, you know, um, in reality. The hard part though is that often these days hardware is really cheap, so a lot of problems, particularly for small and medium businesses, are often just solved by um, better hardware. Because frankly, hardware is cheaper than you writing code a lot of the time. That's the reality, unless you're dealing with some serious scale. So keep that in mind too for all of you as you delve out into the real world. A lot of the time, you'd be amazed how often the priority is not to pay you potentially tens of thousands of dollars of salary to optimize something, as opposed to just tweaking up the dials on the hardware to make things run a bit faster, because that all gets you to the same point. Blake says, I've been doing assignment 2 locally and I don't know how to test it on the CSE servers. I'm not sure what you mean by that. If you want some help, post on the forum. I'm not sure if you mean how to move the files there, or if you mean how to test it, but yeah, just post on the forum if you need some help with that. Other than that, thank you everyone, and hope you have a great day and weekend, and you still have like 2 weeks until assignment 2's due, so plenty of time, but yeah, otherwise I'll see you next week and we'll do our last full week of content, and thanks again, and don't forget to... Actually, there's no feedback for this lecture. Yeah, that's it, Alec. Exactly. So, thanks everyone, and I hope you have a great afternoon.